This is a talk a bit different from what we have seen, because this discussion came out when a particle physicist like I meets astrophysicists, cosmologists, and we start discussing about all this kind of matter, because we talk a lot of dark matter in our particle physicist community. And what I discovered that particle physicists have ideas about dark matter that doesn't match exactly, I would say, not at all, what are the ideas of dark matter that astrophysicists and cosmologists have. So when the two communities, and unfortunately the two communities are not talking, they're kind of very closed communities, and so we talk only through papers and blah, blah, blah. We don't talk really freely. So this is an occasion to see a point of view that is a bit different from somebody that is outside and less technical inside the discussion. So when we talk about dark matter, I want to say that dark matter is something that is absolutely seen in astrophysics. So nothing at all is coming out from any measurements done on Earth. So in this moment, we have a beautiful model for the particles that is called the standard model. So everybody has a standard model. We have our standard model. And in the standard model of the particles, we don't see any deviation. Unfortunately, when you look to the Lagrangian of the standard model of the particles, it fills up a full page, A0 full page with all the terms. That tells you with more than 20 parameters that have to be calculated by experiments. So this is the basics of the standard model. So it looks like that is something that is not definitive. It's something that is an accurate calibration of several pieces put together. And when we look to the experiments we are doing, LHC, but also other experiments, cosmic ray et al., when we go in there, we don't see any deviation. We have tuned these parameters so finely that everything works perfectly, okay? Actually, the only thing that I can say up to today, the only two tension between the fine-tuned modeling are the measurement of the W mass, which is from CDF, which was appearing, it's very nice measurement. And we see that it's 7 sigma out of the standard model prediction. Also, this year, Atlas came out with another measurements that was reducing the tension on this measurement. And also the mu precession dipole momentum measurements that G-2 at Fermi has been done gives you a tension that right now, last year was 4 sigma, now it's increased to some kind of discovery level, which gives you a hint of new physics behind it that is not accounted in this fine-tuned multi-parameters matrix, and is hidden there. Now, dark matter, as you have seen now, in these 2 days of talk, everybody of you knows, instead in astrophysics, something that is well established, I would say. In fact, the physicists, the particle physicists started saying, okay, we start searching dark matter with our instrumentation, underground, in LHC, in other experiment, blah, 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 blah. Yeah. So, for the particle physicist, when you talk to them, they say, okay, what we have a relic density, and for the particle physicist, the relic density is the measure the major parameter. So anything that is not really interacting with standard model particles can be dark matter if we can create enough relic density at the beginning of the universe. So with this paradigm, we can fit from almost zero mass particle like axions to even solar masses object. I've even seen somebody that is proposing like galaxy masses, 10 to the 10 masses particle to fit a kind of dark matter. And but at certain point came out from particle physics, actually, the so-called WIMP miracle. And WIMP is tied, W means weak, so weak force. That is a short range force. And with this trick of the short range forces, you can create naturally a relic density. Actually, in the past, I would say not so fast, much time has passed since there, like 10 years, everybody was thinking that the supersymmetry was true. So everybody thought, okay, we build a new machine that is called LHC, we smash protons, and in a matter of 1 year, 2 years maximum, we get supersymmetry. Actually, this didn't happen. And now supersymmetry is really ruled out because this energy scale of the supersymmetry is so high that somehow doesn't solve the problems that were by which the supersymmetry was thought. Okay, so actually the supersymmetry believers today are few renegades, but basically the supersymmetry, yes, can exist to up energy scale that doesn't really tell you anything on the standard model deviation. Now, the question is, why the WIMP miracle maybe is working in a different way, but with a different initial letter, not W, but something more exotic. There is an idea how we can restrict our dark matter searches, but also modelizing at the sense of the particle. So in this talk, I'm not talking about modified gravity, because as you have heard before by Gowry, by others, somehow modified gravity has some problems to explain many aspects of the observation. So I'm talking about a dark matter that is a new matter that is filling the universe. So the idea that came out discussing also with Paolo is why, because in this moment we have a plethora of models for particles. So every theoretician that come out from the particle physics world come out with an idea, like black holes here and there, new models, fields, blah, blah, blah. So you can fill up with hundreds theories. And what we do basically is that in the experimental community, we look to these models and we try to build experiments that sometimes are very expensive to look at these models, let's say. And the discussion now came at these levels. Why we don't start instead to look more deeper on the only place where dark matter is existing, is seen, which is astrophysics, and try from all the possible observation and correlation at all scales to restrict the number and the type of possible models. So just changing the paradigm of up-down, that means I have a beautiful theory that has something invisible, and this can be dark matter, so try it. Instead, we have a lot of beautiful observation and try to find a way to arrive to something that is reasonable, that can, in principle, as soon as you make your theory, have to fit all the possible observation. And I would say that the observations are increasingly detailed every day. Okay, this is the idea. I make some example that everybody knows, but Gauri has shown it. Here we have a plot that from Paolo. And you see that there is a beautiful correlation up to several order of magnitude of masses of galaxies from dwarf galaxies to M87 between the core radius and the luminous radius. And I mean, for me, this correlation is striking in the sense that when you start thinking too many of the possible explanation on the core structure, I mean, you have to find a way, a simple way to make this correlation be really appearing naturally, okay? Not something that you have to modelize finally galaxy by galaxy, etc. I mean, it cannot be. Otherwise, you should have seen a distribution on these two quantities that you should fill up this plot. But another striking thing on the spiral galaxies is what Gauri has shown more in a previous talk. It's the core structure and the existence of a universal rotation curve. I mean, that is, apart from some funny galaxies, but most of them, I mean, we can modelize very simply with an universal curve, so a couple of parameters, and we know exactly which is the density of the dark matter. Here, some observation we made with Paolo using universal rotation curves. And when you look to the quantity that is the product of density of dark matter and density of barium matter at the core radius, nearby the core radius, this product looks like a constant all over the galaxy up to several order of magnitude of masses. It's a factor 2, if you between 2 and 3, the same number. Now, I'm a particle physicist. When I think of this quantity, I look to a beam of particles impinging to a target, and I calculate the rate of interactions between the impinging beam to the target. And this rate of interaction is actually proportional to the product of the density of the beam and the density of the target. Here we plot also the square of which is KSA, the square of the density of dark matter at the core radius, and you see that it changes a lot. This is a value that is proportional to self-interaction of the dark matter at the core radius. Okay, so to me, this observation, it's likely telling me, coming out from technical astrophysical world, that maybe there is a direct interaction between the two, which is not only gravitational. It should be something else. Is why we started talking with Paul about collisional dark matter. Another thing that is striking to me is the observation of Gauri. This plot we have seen from Gauri. In this plot we see that z equal 1, Gauri, if I'm not wrong, we see a core that is smaller and larger density. This tells you this plot. So when you think about it, you come at very, very simply to a picture like this. So you start at the beginning with a pure NFW, which is non-collisional density structure, and then you start having a kind of depletion, which is secular. So takes an Hubble time to develop up to today. And so what you see is the core that starts developing with time, until we reach our days. And what we see at the neck, where the core starts, this product, which is the product of dark matter density and baryon density, is a kind of threshold where the interaction between the two worlds is somehow significant for the evolution of the halo. And this way, you create naturally all the structure that are coming from small galaxy up to bigger galaxy in a natural way. I mean, you don't need to make a fine tuning. So this is an example. I mean, there are many other observations that are coming out where correlation can be put together. And in this way, if you believe that this observation are telling you something, for example, one very simple thing we were discussing with you a couple of days ago, axions are not fitting the picture. One thing, because bigger galaxies have smaller core, and the smaller galaxies have larger core. So this correlation is absolutely not existing. The first plot. So you can somehow discard this kind of model. From discussion, I've understood that warm dark matter, although it's working, but you don't know how much is the density of warm dark matter from different galaxies. How can you fit this large scale structure from small to large? I mean, at the beginning, you can have different fractions of the two components, but at the end, you start evolving in the same way, and only the product of the two is giving you a threshold, okay? It's the abundance, relative abundance of the two that gives you the dimension of the core. And so forth. So also, if you use machos, black hole, or primordial black hole, and so forth, all this one for sure will fit up the NFW up to the present days, because I mean, not even the baryonic feedback can ensure the depletion of the central region. So I mean, you see that when you start putting together all the observation, you start really fast to start excluding a lot of model, a lot of even WIMPs. You will see can be somehow ruled out. So from my impression, from outside, I would say to this matter, I say, oh, the best way to fit the picture is to have particles that are somehow heavier, some keV, so heavier than warm dark matter. Then I have the idea that this constant, so the product of the two, the density of the two components of core radius, give us me idea that there is some kind of interaction between the two species. And so having a collisional dark matter can solve naturally the problem of the cores, but maybe can solve other problems, because in this case, at large scale is cosmological scales, the densities or relative density of the two components are so low that lambda CDM is fitting well the observation. So CMB observations are perfectly fitting this this kind of picture. Okay, we don't. So how can we deplete the central region of the galaxy? So we can exchange momentum with hot galactic spots and warm up the dark matter. So we are depleting just by pulling out the dark matter. We can have some pit where the dark matter is falling and start annihilating, and so you deplete it. But also, even if the dark matter is falling some pit that is some object, you don't see it anymore as dark matter because you see as a mass of the object. So you hide it, even if the dark matter is still existing. And then we can think about direct dark matter and baryonic matter. Just to tell you, this is a value that Paolo found, that we don't need much energy to deplete the internal core, okay? So we need some energy exchange, some momentum exchange, and then puff, the dark matter just escape from the central region. So one way that is interesting is the slingshot. Actually, if you look to the models that are used for simulation, it exists a kind of parameter that is called softening. So when two stars or dark matter particles get too close, you just put off the gravitational force, and then they pass through like there is nothing. Instead, when you go close to a star, you get a kick. We're using it to send satellites to Jupiter and here and there, the same trick. So the heavy object gives a momentum to the small object. So this is not modelized, for example. We can have a heavy object that starts sucking dark matter. Unfortunately, you make some calculation, you see that gravitationally a star can, like a sun, can suck up to 10 to the minus 10 dark matter particle because of density problem. So this is not sufficient. So you see that in this way, it's you start to look into this problem, and you see that it's not easy to solve. Annihilation. Annihilation can happen only since we are thinking to a kind of paradigm similar to WIMP. Then you say, yes, I have to create a region where density is enough high to start annihilation. Okay, but somehow we can have some relic annihilation is what we are searching. Wake interaction. I mean, I cannot say wake interaction. For me, wake interaction is ruled out as a particle physicist for this kind of scenario. I'm a believer that there is another sector with larger masses that we don't see again, and we have a short range force between the fermions. Matter to me means fermion, being a particle physicist, but can be anything else. And what we do in particle physics, we search for portals that are going from standard matter to invisible matter, what we call dark matter. Unfortunately, in experiments like LHC, to do this, we search for a large momentum anisotropy from what is triggered by the experiment to what is invisible. So there are some kinematical conditions where actually this doesn't happen. I call it on the threshold. So the momentum is so low that the background is just make your search blind. You would see these searches by Marina Kobal in a few days, and you see that their searches on large missing ET are called. Actually, we have another way to look at it where we have photon-photon fusion. In fact, I added here photons, photon-photon fusion. If we have a portal like axion-like particles that dig into the dark matter, sector, here we have enough power to disentangle also events where the missing it is not so large. So about direct searches, so WIMP search are basically based on nuclear recoil. So if this doesn't happen because the kinematics are a bit different, you don't see it basically. Now, if I look to the Pamela positrons, we had the talk yesterday about Pamela positrons. I mean, if you look to Pamela positrons, you should have a mass that is above 400 GeV and goes up to the TV. So this is a possible, this is an observation. So I'm looking to the observation. And another thing that we can do is try to see an annihilation of dark matter close by, because if dark matter is so heavy, we should have a large shower around you so you can see the muons coming out from the point where the annihilation is happening. So maybe object with large volume of observation like neutrino experiments maybe can tag some of these annihilation events inside the volume. Actually, what I can say is that if it's true that the annihilation is dictated by density, this should happen if the annihilation is doing this. We should expect that it happens inside heavy objects, so we don't see it basically. And this is why we don't have a large signal from annihilation, and this is why we are struggling a lot. You have seen talk yesterday about this to find an indirect signal. Now I put you a provocation, call it a provocation. Just to correlate the two components, we had just some friction between the two components. So a viscosity, and in this case, we compacted the dark matter halo in the central region to the disk. We increased the local density by at least a couple of order of magnitude. So something is enhanced between the previous discussion on the interaction. But can we see such a particle with the present detector? I would say no, because we expect that in this region where we are sitting, the dark matter is thermalized with the local baryon matter. So the speeds that we foresee are very slow. So that's basically the speed of the Earth turning around the sun. This is so 1 order of magnitude speed less. The density is still small, and to catch it, we need large volumes. And the annihilation is not happening outside mostly, so we don't see it very easily. And it's only a small part has been seen, so it contributes to the Pamela positron excess. I would say that in this scenario, the annihilation signal from gamma ray should happen in regions that are not compact region. Of course, we need a cross section which is close to the nuclear cross section, which is absolutely enormous. So any particle physicist theoretician will jump on the seat. So we'd say it's not possible at all. And it is partially in contrast with the bullet cluster observation. So, but in fact, I said at the beginning, a provocation is not a real model. So I'm jumping to my conclusion. My conclusion is that we should look to the astrophysics and observation more in a more extensive way to constrain the modeling of dark matter. Yeah, I don't cover all the possible aspects of the phenomenon, and I'm trying to apply kind of mediocrity principle. That means the simplest, the better. And of course, this is a work in progress. And given the fact that we are getting better measurements from day-to-day, better observatories every day, so we will have more guidance on this matter. And that's all.